Bingo.
There we go.
Webinar is now broadcasting to all attendees.
That's right. And so they'll have, I guess they're in a waiting room or something, and then they just start to filter in. So,
alrighty.
Yep, there they are. So.
Okay, so if I click on that, then I'll see those names.
You'll see the names. Mm-hmm.
Okay, all right, wow, okay.
There you go.
And they can hear me now.
They can definitely hear you now.
All right. All right, well, we're not starting yet, but just welcome those who are trickling in. We've got a few more minutes before we'll begin. But you know, the seats are getting filled. I hope everybody's 6 feet apart.
That's right. It's important. There we go. Okay.
The nice thing tonight is supposed to be clear.
It's cleared up where I am. So I'm in San Bernardino, and it's gotten pretty clear outside.
Yeah,
so.
And so actually Belmont says cloudy at the moment.
At the moment.
But it's predicting clearness, which is good because like at the end of what I'm going to share with everybody, I'm going to share a little bit about, you know, the night sky tonight. And I don't want to give it away, but there is something special happening tonight.
Oh, didn't know that. Excellent.
Yep.
Excellent. Wow.
Okay, so we're up to 20 people.
I know.
2 minutes to go, and maybe we'll give everybody a gracious minute. 7:01.
That's right. Okay. And for those of you who sent questions ahead of time, I do have the list here. So I will be also monitoring other stuff, the chat and the Q&A as well, but I do have the questions that were sent to me ahead of time so that we can make sure they get answered or at least addressed.
Yep, and I'm happy to answer more questions. You can type them into the chat along the way. I enjoy interaction. And after we start, people can still pop in, true?
Absolutely. Yep.
Yeah.
Yep. We've had cases where sometimes somebody just gets bumped out accidentally, and then they come back in, and then other times when people register at the very last minute and then enter right then too.
Yeah. So yeah, I know about that because teaching with the kids at home, yeah, sometimes who knows what happens. They get bumped out and then they bump in again. And some of my students are like, you know, appear like twice. They have their computer on and they have their cell phone on in case something happens. They're kind of like double covered.
Mm-hmm.
Yeah. Technology it's really neat what we can do. It really is neat. I mean, I remember years ago trying to figure out, well, how does Skype work? And now, you know.
And now you do it every day, huh?
Yeah, now I'm like a Zoom pro.
Okay.
And Google Meet also, so.
There you go. Multilingual, huh?
Yep. Yep. You got to find your way around in this coronavid world.
Okay. So I just want to welcome everyone. I know we're still going to give them another minute or two before Dave starts. My name is Mirka Zaplatel, and I'm the Director of Education at the McAuliffe-Shepard Discovery Center. So thank you so much for joining us for another one of our Superstellar Fridays. We can't get together yet, but here's a way for us to still learn about some fantastic science from the comfort of our own homes, or it's my basement in this case. As I mentioned before, I do have some questions from people that sent them to me ahead of time, but we've got the chat open and there's also the Q&A option for you. So if you have a question, you can type those in there. If you see that someone else has a question you have as well, you can say, hey, that also applies to me, or you can vote for it in the Q&A. And this time, we haven't done this before, but we're going to try it out. If you would like to actually speak your question, we're going to try having you raise your hand. And when we see the hand is raised, we can unmute you and then you can ask the question. So you've got a number of different ways when you have questions. And for those of you who are using the chat for the Q&A, Dave will stop periodically and ask me if I have any questions to pass along. So even if we don't answer it as soon as you type it, just know that I'm keeping track of everything. And hopefully we'll get to them all. I know that I'm really excited because we haven't had an astronomy one in a while. So we're going to be talking about the night sky again. And every time that Dave tells me something about the sky, I learned so much because he's got more knowledge about the night sky than I have forgotten at this point. And so I am so excited about this. Dave McDonald is one of our educators, as well as doing a number of other things. He's involved in the New Hampshire Astronomical Society. He is a teacher at Belmont High. I'm sure, I found out the other day he's a pilot. So there are just a number of things that he does. He has a huge amount of information, and I know it's going to be a fantastic presentation. So I'm going to turn it over to him, but just know that I'm here paying attention to your questions, that kind of a thing as we go through the presentation.
Well, great. Well, thanks for all that, Mirka. It's always good to be here. And I'm happy that some of my astronomy students have joined in. And welcome, everybody. Glad that you're able to make it tonight. And we're going to take a kind of a quick tour of the night sky, like what's involved in looking at the night sky. Because so often we go out our kitchen door and maybe we look up and say, oh, look, there's stars out tonight, or it's cloudy tonight. But we don't take time to really observe. And so I hope I'm going to share some things with you that you will learn and enjoy and be able to try, practice, and that the night sky will become a familiar friend, if you will. So I'm going to start presenting. I've got a few things to present. So I got a lot of buttons down on my tray and such. So I'm going to be looking around and trying to find the things that I want to share and all. So I'm going to start by sharing my screen fully, like so, and then I am going to choose my presentation, and hopefully everybody can kind of see that full screen. Does everybody see that? Mirka, can you confirm that people can
Yep.
see my screen?
I see Superstellar Friday, Understanding the Night Sky.
All righty. So that's what we're talking about. And as Mirka said, I do a few things related to astronomy. I am an astronomy instructor. I've taught at NHTI, Lakes Region Community College. I'm STEM astronomy instructor at Belmont High School, senior educator at the McAuliffe-Shepard Discovery Center, and member of the New Hampshire Astronomical Society. And Elena has a question, it seems. So Mirka, you'll have to get the question because I can't go back and forth easily from my screen to any questions. So understanding the night sky is the topic. All right. So we can try this.
So if Elena has a question, I've now, let's see, I'm going to ask you to unmute.
Yeah, I'm pushing that. It's not doing anything. Unmute. Yeah, it's not changing.
So maybe on Elena's end, then she needs to unmute herself, I think.
Perhaps.
Why stars in outer space?
Yes.
And
So,
why is outer
Wait, can't see if they can hear you.
why
you know,
is
we can hear.
Go ahead.
why is stars in outer space?
Okay, well, you listen, and I think you're going to find the answer along the way here. So we're going to start. This is kind of what we're talking about, which is relative to your question. Talk about constellations, asterisms. I think for a lot of you, that's going to be a new word. It's a very important word. A distance to different things out there, a magnitude scale, which has to do with the brightness of objects. Stars have color, the celestial sphere. And what's up? We're going to take a little time towards the end to kind of look at, well, what's up? And there's something special happening tonight that you won't want to miss. And I think it's supposed to be clear. So that's kind of cool. So the first thing everybody tends to think about in the night sky is constellations. So what I have here in the upper left, you see, is the constellations of Sagittarius, which is the Centaur Archer, and Scorpius, the Scorpion. And these constellations, we're getting the very last looks of them. Sagittarius is up for a bit. Scorpius is just about out of sight. In the southern sky, you can find these constellations. We're going to talk a little bit more about them in particular later. But the whole idea is that in ancient times, constellations only referred to the brightest stars that appeared, and they represented mythological figures. The Babylonians, like Baghdad, was actually a cradle of astronomy. And the Babylonians, the Arabs, they seem to take a liking to naming things and naming stars. And then subsequently, the Greeks and the Roman, with their mythology, kind of started visualizing these pictures up there. Because remember, if you go back 4,000 years ago, they had to watch television by candlelight. So what was there to do? Video games were not invented yet. The image I just brought up on the right side of the screen is another timely image from the standpoint. I'm going to kind of use my pointer here. And maybe you can see upside down is the horse. It's Pegasus, the flying horse. And then these four stars that I'm kind of outlining are making up the great square of Pegasus. And then if you look in the square going to the upper left, there's some stars, and it kind of looks like, well, look, there's a woman there. Well, that's Andromeda. That's the daughter of King Cepheus and Queen Cassiopeia. So we're going to talk about this a little bit later, but that's just to say that these constellations have been going on for thousands of years, particularly in the northern hemisphere. If we had time, another time, maybe we would like to do a presentation about the southern hemisphere. A lot of the southern hemisphere constellations have more modern names like microscope, compass, things of that nature, because they're more modern in nature. Well, I mentioned that word asterism. So an asterism is a familiar shape which may be made up of stars from the same or from different constellations. And here's a shocker: the Big Dipper is not a constellation. It's an asterism. It's a familiar shape, a dipper. For us, it's a dipper. For people in France, it's the saucepan. For people in Italy, it's like a cleaver. For people in the UK, it's the plow. So we see these stars and we make up these asterisms, which are familiar shapes made up of stars that may or may not be from the same constellation. So the great square of Pegasus I just showed you, I'm going to show it to you yet again, borrows the brightest star, Alpheratz, from Andromeda. So the great square of Pegasus actually only has 3 stars from Pegasus and 1 star from Andromeda. And that's the brightest star in the square, Alpheratz. And the way I remember that is I just picture a huge rat, the Alpha Rat. So this is the Big Dipper that we're looking at here. And when we see the Big Dipper up in the sky, we need to realize that the stars are not all at the same distance. Like years ago, they thought they were painted on what was called a celestial sphere. But they only appear to be close to each other because if you look down where it says nearest star and farthest star down here, you can see that they're at varying distances. Several of the stars are very similar distances, but you can see there's a nearest one, there's this one here, which is named Alkaid. Alkaid is one of my favorites because it's 100 light years away. It's like the century star, the 100-year anniversary star. It's kind of cool. And the farthest star away is Dubhe or Dubhe. And then we have the fact that it's just like a projection effect that we see, but in reality, if we had a spaceship and flying among the stars, they would look entirely different because they're at different distances from us. And again, the Big Dipper is an asterism. It's part of the constellation we know as Ursa Major, the Big Bear. It's part of a constellation. Then I mentioned the square Pegasus before. So you look at these zigzags here and such. So back in the early 1930s, the International Astronomical Union, the IAU, made boundaries for all the constellations. And just like there are 88 keys on a standard piano keyboard, there are 88 constellations in both the northern and the southern hemisphere. About 67 of them show up in the northern hemisphere at one time or another, and I think at most around 40 at any one season do we get to see. So again, all the constellations, all 88 of them have a boundary. Why there's so many zigs and zags, that question I do not know. But here's the great square of Pegasus, and you can see 3 stars in Pegasus, and this one right on the edge is in over the line into Andromeda, Alpheratz. And then we have the constellation of Andromeda. We're going to talk a little bit more about that a little bit later. And as again, she is in mythology the daughter of King Cepheus and Queen Cassiopeia. This is a photograph of the constellation Orion, which is a winter constellation, but if you stay up late enough, like 1 o'clock in the morning, you know winter's coming because Orion is starting to make an appearance around 1 o'clock in the morning. So that's a photograph of it. And the reason I'm showing you this is to point out names. Stars have names: Betelgeuse, Rigel, and the constellations also get Greek names, or Greek letters. And typically, the Alpha star here, that's the Greek letter Alpha, and the Beta star, the Greek letter Beta, and then you have Gamma, Delta, Epsilon, Zeta, Eta, Theta, Iota, Kappa, Lambda, Mi, Ni, Xi, Omicron, Pi, Rho, Sigma, Tau, Epsilon, Phi, Chi, Psi, Omega, 24 letters. And typically it's the order of brightness of the stars, but sometimes it's a little off. As a matter of fact, in Orion, though Betelgeuse is the alpha star, it's actually number 2 in terms of its brightness, and the beta star is actually brighter. But when these things were labeled with, they're very close. So when these stars were labeled with the Greek letters, they didn't have the metrics that we have these days and the quality of photometers and such that can measure brightness to very, very accurate numbers. So that's one reason why it may not be exact in the order. But anyway, the brighter stars get Greek letters. And we've got 24 of them to choose from. Arabic names are very common. This happens to be Libra, which is, as you would look south at Scorpius, it's to the right or towards the west of Scorpius. And so it is really setting, hard to find. But I really like these stars' names. So there's Zubin-e-Shamali and Zubin-el-Ganubi. They're Arabic names going back 4,000 years ago. And what they mean is northern claw and southern claw. Zubin is claw, and then you see the Eshamali and the El-Ganubi, and that's northern and southern Arabic names. So even though Libra doesn't have claws, those stars used to be the ends of the claws of Scorpius. And then another story to get into sometime, the Romans in Julius Caesar's time, and rumor has it was his doing, cut off the claws of the scorpion so that Libra could be more pronounced in his honor of being the the person of justice and all. So Libra with some Arabic names. And then we have the star Antares, and that's the heart of the scorpion. We're going to talk more about Antares a little bit later. And then these are the stars of the Big Dipper. Again, Arabic names. I'm not going to go through them all. Again, this is one of my favorite stars, Alkaid, because it's 100 light years away. I call it the century star. And then we have Merak and Dubi or Dubhe, and these are the pointer stars that if you were to follow them about 5 times that distance, you're going to end up at the North Star, Polaris, which is not Arabic. And we'll talk a little bit more about that later. So names of stars, they get Greek letters for the brighter ones, and they get Arabic names. Some are not Arabic, but again, back in Babylonian times, what are you going to do at night? Let's look at some stars. Let's make up some names. Stars have colors. Now, I'm not going to go into detail about this. This is definitely a diagram from my astronomy class, and maybe some of you have seen it before. It is like the most famous piece of information, the most famous diagram in astronomy, called the Hertzsprung-Russell diagram, named after, guess who? 2 gentlemen named Hertzsprung and 1 named Russell. And basically, in a nutshell, on the left side has to do with brightness relative to our sun. So right here, you see the number 1. That's assigning the value of our sun is like 1 level of brightness, and then everything will be measured by that. So you see, if I come across right close to the middle, there is our sun. Then if you look down the bottom, you see there's some colors going on here. And at the far right, you have 2,000, and coming over towards the left, 30,000, and there would be more numbers going up to 50,000 or so. And that's a temperature in degrees, in Kelvin. And that is a scientific temperature scale where absolute 0 is 0. Kind of convenient. Well, the middle curve here is what we call the main sequence. Most stars are on what we call the main sequence. They're burning, they're happy, they're stable. And again, another time we can talk about all the other different flavors of dwarfs and giants, be they red or blue or white. So contrary to what we experience with our heat and air conditioning controls in our car, or even if you go to a hotel, there's the red dot for the hot water and the blue dot for the cold water. Actually, red stars are the coolest, around 3,000 Kelvin, which is still pretty hot, but in the realm of the temperature of stars, it's cool. Orange stars, a little warmer. Yellow stars are in the average range, 5,500-ish, plus or minus a little. Our sun is 5,600 Kelvin, and those are yellow stars. White stars are really hot, around 10,000, about twice as hot as the yellow stars in terms of Kelvin. Then the blue-white stars, they're still hotter. And then when we get to the blue stars, greater than 30,000 Kelvin. So blue are the hot stars, and the red are the cool stars. So when you go out at night, one of your assignments is to notice the stars have color. And if you take some time, you'll be able to get it. Because if you just go out your back door onto your deck, look up for 5 minutes, it's not going to happen. You need 15 minutes, 20 minutes just for your eyes to adjust to be able to detect these things. Because your eyes have what are called rods and cones, are the receptors, the nerves that recept the light, receive the light. And the rods only detect black and white images. They're more sensitive. The cones detect color, and they're not as sensitive. So they need a little time to adjust to the darkness, to be able to absorb the right frequency, to be able to determine, oh, that definitely looks reddish, or that's bluish, or that's yellow. Aldebaran, my goodness, that looks orange. So enjoy learning to look for color in the stars. So there's the brightness, right? Stars are brighter. One is brighter than another. Well, let's talk a little bit about that. So there was this Greek guy, Hipparchus, back 160 to 127 BC, and he was into sports. You may or may not know that the Greeks had what was called the Olympics, and a lot of that had to do with like track and field type events. And you have a race. What place does the winner get? First place, right? And the person who comes in next gets second place. And the next runner, third place. Well, you see where I'm going with this. I'll stop there. Same idea with stars. A first place star is the brightest. That star is the brightest. It comes in first place. Then that star is bright, but not as bright as the first place star. So we'll make that a second place star. And then we have a third place star. And they went all the way down to sixth place, where a sixth place star was a star that you could, on a dark, clear night, you could just barely see. You could just make it out. And so Hipparchus came up with the scale, got his buddies together, and he said, okay, so I've got this figured out, first place stars, second place stars, sixth place stars. Hey, how much brighter do you think a first place star is than the dimmest sixth place star? And so they chit-chatted with each other, and they came up with, and again, remember, they don't have any electronic detecting equipment, no photometers. They're just looking at it with their eyes. And they came up with the idea, I think 100 times. 100's a good number, right? And they thought it kind of applied that the brightest stars are 100 times brighter than the dimmest stars. So that was a proportion, so to speak, that was used. Well, later on, we did develop measuring equipment and photometers. And now we have the ability to determine how, like a light meter, right? How bright are things really? And we could now kind of get really close into the decimal places of tenths and hundredths and more. And we find out that, oh my goodness, these bright stars we have, they're a lot brighter than 100 times brighter than the dimmest stars. So they decided to keep magnitude 6 at the dimmest. So barely can see on a dark, clear night, 6 magnitude, we kept that. They also decided to keep the same scale, that 5 magnitudes from 1 to 6 would be 100 times. The only difference is now we had to go from 1 to 0, and even into the negative numbers. So technically speaking, and I have this down the bottom, a 1 magnitude difference is a factor of 2.512, which is the 5th root of 100, because you've got 100 times you want to evenly divide among 5 places. So the 5th root of 100 is the difference in brightness from one magnitude to another. So there's what's called the visual magnitude, M sub V, and there's what's called absolute magnitude, which is how bright the star really is. And that would, again, would be a topic for another time. But in terms of, oh, I forgot to bring up the stamp. This is the Greek stamp with guess who on it? Hipparchus. And you can see kind of a celestial sphere type of object off to his right. So anyway, if you kind of look at this, we now have more metrics that we can measure. And now we know that, for example, the star Sirius is to the left of 0. It's in the negative realm. As a matter of fact, it's like negative 1.42 or negative 1.44 in terms of its magnitude. We still have the naked eye limit at 6. The Hubble Space Telescope sees down towards magnitude 30. And remember, each magnitude, you're getting dimmer and dimmer by 2.5 times. Going the bright, full moon's about a negative 11, and the sun is about negative 26. And you can see down the bottom, I've got those numbers. Actually, the moon is negative 12.5. All righty, so that is related to the brightness. And so I say current magnitudes because the planets change. So Polaris is our North Star. It's not super bright. It's a magnitude 2. It's like a second place star, if you will. Alpheratz, which I showed you to be the corner, one of the corners of the Great Square Pegasus, is a magnitude 2. I'm not going to magnitude 3, 4, 5 like that. I thought it'd be easier for you to find the brighter stars. Antares, I mentioned to you, is the heart of the Scorpion. And we're going to be mentioning Antares again. As we look at it, the apparent magnitude or the visual magnitude is 1. Deneb is a star in the constellation Cygnus. It's pretty overhead early evenings when it's dark, earlier in the evening. It's almost directly overhead. That's Deneb. It's the tail of Cygnus, the swan, or the top of the Northern Cross. Magnitude 1 for it. Then we have Vega and Capella. I chose these two because Vega rules the summer sky, happens to be a blue-white star, very hot. And it's a magnitude 0. It's still out. You can still see Vega, still very bright, but it's making its way towards the western horizon. And then the harbinger of winter, Capella, is on its way up, rising in the east. They're not exactly opposite in the sky, but they're kind of close to being opposite on either side of the North Star. And Capella is a yellow star, like our sun. It's yellow, medium temperature-ish, around 5,500 Kelvin. Magnitude 0 for both of those. So they are 2.5 times brighter than Antares and Deneb. The brightest star in the night sky I mentioned is Sirius, and that's a winter constellation in Canis Major. Negative 1.42 or negative 1.44, I think may have been the latest number I saw. Brightest star in the night sky. Well, yes, things get brighter. Jupiter and Mars are out, and I'm going to show you where to find them tonight. And Jupiter and Mars are at a negative 2.5. Both of them. Jupiter, more on the whiter side as you look at it, because it has the clouds are reflecting more of a whiter light. And Mars, definitely reddish in color. And again, Stars have their own nuclear furnace. Stars create their own light, their own energy. Planets reflect light. So the temperature paradigm doesn't work for planets the same way because planets reflect light. They do not generate light. But Mars has a reddish surface. Iron oxide, rust is a predominant on the surface of Mars, so it reflects a reddish color. Saturn, kind of yellow in the sky, not anywhere near as bright as Jupiter and Mars, but plenty bright. It's a magnitude 1/2, so it's a little dimmer than Vega and Capella, but brighter than Antares and Deneb, 0.5, and kind of a yellowish color for Saturn. And then blazing Venus in the morning sky. If you go out an hour and a half, an hour before the sun rises, look in the east, and Venus is blazing, magnitude -4.5. It's hugely bright. It's making its way back towards the sun. So it's visible, I think, for another month or so. You'll be able to find it in the morning, but every morning it's getting a little closer to the horizon. Okay, in a moment I'll stop for questions. While we're talking about the planets and the magnitudes, and Mars again is a -2.5, thought I might talk a little bit about the changing size of Mars, because Earth obviously is orbiting our sun. It goes around in about a year. Well, we define it as being a year. And Mars is further away. It's about 50% further away than Earth is. And Mars also orbits the sun, but at a slower pace. So when Mars and Earth are closer together, Mars appears bigger in a telescope. When Earth and Mars are further away from each other, Mars appears smaller. So here are some samples of actual photographs. And you can see how Mars, as gets closer to Earth, gets bigger and bigger and bigger here. We're facing south. And then after we have the closest encounter, if you will, Mars gets a little smaller, 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 smaller. Well, the closest approach, and this is the neat thing about having this tonight, October 2nd, because just 4 more nights, October 6th, is the closest approach of Mars and Earth. They're going to be as close as they're going to get this year. And so if you have a telescope, have a look, because I think it's going to be about 23 to 25 seconds of arc, which is for another time something else we could talk about, how large things appear in the sky and through a telescope. But when you look through a telescope, Mars is going to be really big for a planet looking through a telescope, October 6th. October 13th is another benchmark. That's called opposition. And what opposition is, I have it down at the bottom, that is when you have the sun, Earth, and whatever the object is. In this case, we're talking about Mars. So sun, Earth, Mars. Direct in a straight line, one opposite the other. So when the sun sets, the object in question, in this case, Mars, on October 13th, when the sun sets, Mars is going to rise. And that means it'll be up all night, and around midnight, depending upon your exact longitude, around midnight will be its highest in the sky. And that's one thing, because 2 years ago in 2018, we had a nice close approach with Mars, but it was lower in the horizon, above the horizon. So we got like an extra 30 degrees of height, so to speak, or altitude from where we were 2 years ago. And so Mars is really in prime viewing position October 6th to October 13th. And, you know, another week or two after is still good. You're not going to get it this good again until 2035. You're going to have to wait 15 more years for it to be this good. So catch it this month, and you'll enjoy it. All right. So I'm going to stop there and for a moment and see if there are some questions that you might have, and then we'll continue. Got more things to tell you, and we're going to show you the night sky, but we'll stop there for a moment and see if there are any questions.
Yep. So Dave, you do have a few questions right now. So first of all, we have, why are the names of the stars typically Arabic?
Well, the Arabs, or the Babylonians at that time in what is now Iran and Iraq, and you know, where the Tigris and Euphrates rivers are, Mesopotamia, they seem to be the first ones that cared. And so I guess if you're like the first to name something, you get to name it. It's almost like comets these days. If you discover a comet, you get your name attached to it. If you discover an asteroid, you get to name it. And so again, 4-ish, 5-ish thousand years ago, the people in Babylonia, Mesopotamia, the Arabs, cared enough to kind of make some maps and put names on them. And so they've just stuck. Nobody's felt like they wanted to insult anybody and change the names. There are a few stars that have not Arabic names and may have more modern names, or they got changed. But most of the original Arabic names remain to this day.
And then we have some questions about actually looking at the sky itself. Why is Sirius a winter constellation if it's the brightest? That's coming from Elena again.
I knew that was going to be Elena's question. I knew it. I'm going to explain that coming up. I will be explaining that. Excellent question. But the answer to that is coming. I have, you know, kind of an illustration to help explain that one.
Okay. And then we've got, I think, a clarification question. So Mars will be in the southern sky or midway is the question.
Southern sky. It rises like south of east, and it will move across from southeast to southwest, and it will be crossing the southern sky. But right now, it rises around 8 o'clock, depending upon how flat your horizon is, because if you have trees or a hill or a barn in the way, then you got that to deal with. But if the horizon was flat, around 8 o'clock, Mars rises. But as I said, on October 13th, when the sun sets, Mars will rise. So you can look up sunset time, which I haven't, but what's the sunset time on October 13th? And that's going to be Mars rise time on October 13th. And then it's going to come up towards the southern sky, so around midnight. If you look pretty much south, it will be as high in the sky as it's going to get. And that would be the ideal time to take out your telescope, will be around midnight or so on October 13th, or the week from October 6th to October 13th. Because again, there's an advantage in being in opposition, being directly opposite the sun, getting the full force of the sunlight. But there's also an advantage of being a little bit closer on October 6th. I hope that answered your question.
Well, I think that there's a follow-up. So how high is that?
I think it's going to get up to about 60 degrees up. Okay, so from like straight, I'm not sure you can see what I'm doing, but straight out to the horizon to straight up overhead to a point we call the zenith is 90 degrees, makes a right triangle. So a little more than halfway up, Mars will get up there.
So she said, thank you for that answer.
You're welcome.
Then we have two questions that are a bit more about kind of the structure of what's out there. So one question is, what are stars made of?
Hot gas. Technically, a plasma. depending on how much you might know about atoms and the nucleus of atoms. You know, we have protons, neutrons in the nucleus of atoms, and we have electrons that orbit the nucleus. And when things get really, really hot, like the temperatures that happen in a nuclear furnace, like we have nuclear fusion going on in the stars. That's what powers them, nuclear fusion, and really, really hot. And so it's the fourth state of matter, because you're familiar with solid, liquid, and gas. When things get even hotter, they become a plasma, where the parts of an atom kind of disconnect and get very soupy and hot. So a quick, simple answer: what are stars made of? They're made of hot plasma gas. And depending upon the exact nature of the star, could be different elements. The most predominant element in a star is hydrogen. And the nuclear furnace is fusing hydrogen to create helium. And then depending upon how massive the star is, it may be able to fuse helium to oxygen and carbon and silicon. And if you have a massive, massive, massive star, it can fuse to the point of iron. And that's where it stops. No elements beyond iron can be made in a star, because there's not enough heat, there's not enough pressure. You have to add extra energy to get beyond iron. And that's where supernovas come into play, because they provide the extra power, if you will, the extra heat, the extra energy to continue to fuse iron and other elements into the heavier elements that we have in our universe.
And then this was asked, I think, in response to hearing you talk about what stars are made of. If our sun was a white star, how far would the Earth have to be away to survive?
I never calculated that, and I've never been asked that question before. You know, I've been doing this for a lot of years, and I've never been asked that question. That would be a great problem to figure out. So I can't do that in my head. Obviously, the answer is further away than we are now. So that's a very interesting question. So if it became a white star, so if we doubled the temperature, okay, then we're going to have to be at least twice as far away. So we're 93 million miles away from the sun on average now. So 186 million miles would be a reasonable guess. Have to get my scientific calculator out. That's a great question, very creative question.
And then I think one final question for this section, and I'll save the others for later, but going on with the structure of what's out there, someone asked, why are there so many planets in our solar system?
Well, I guess saying there are so many is kind of a relative term. We have planets from Mercury out to Pluto. That gives us 9. We have Ceres as a dwarf planet, which is the largest asteroid. Beyond Pluto, we have Haumea, Makemake, and Quaoar, and Eris. Eris is twice as far away as Pluto, and not quite as big, but Eris is kind of what started the whole dwarf planet definition thing in a way. That's a topic for another time. If you got a couple hours, so happy to talk about that. So, you know, we've got, let's just say 16, 17-ish planets, including terrestrial planets and Jovian planets, which are the gas giants, and then the dwarf planets. Other star systems may have more, they may have less. we have discovered thousands of planets around other stars. But in terms of like, why do we have the number that we have? Well, when the nebula that we were created from the gelling of the material that was there, that was closest to the sun, heated up and got molten, and then different aspects of the conditions, which obviously I wasn't there, created planets that were at different distances. And we know that largely rocky planets were closer to the sun. You have Mercury, Venus, Earth, and Mars, rocky planets. And then you have this zone of the asteroid belt. And beyond that, you have now the gas giants, Jupiter, Saturn, Uranus, and Neptune. And then beyond, and those are gaseous in nature, and they're big, called gas giants or Jovian planets. And then we kind of get back to rocky, icy stuff like Pluto and other trans-Neptunian objects. And it's all related to how much stuff there was when our sun was created, and what stuff was not used in the sun, what stuff was left over, how far away the material was, how hot it was. And the angular momentum is conserved. All the planets rotate around the sun in the same direction, counterclockwise, as seen from above. I hope that was a decent stab at your question.
Okay, I'm sure that they'll follow up if they have more that they'd like to know. So the remaining questions that we've got right now are very much about when you look up at the sky, kind of how you're doing that. So I think maybe we'll save them for the next break.
Okay, great. And we are definitely going to get to looking up at the sky. All right, so great. We'll continue then. I'm not going to spend a lot of time with the celestial sphere, just a couple of definitions, because it may be helpful in explaining about the star question, like why Sirius is up in the winter, for example. So you can see my pointer here. We're on Earth. We got a little guy on Earth here. Earth's axis is tilted. This is a little exaggerated. We're tilted at 23.44 degrees. And the rotational axis of our Earth points to the north celestial pole, which is where Polaris, our North Star, is located within 3/4 of a degree. It's there. Wherever you are on Earth, if you look directly above, that's your zenith. And if you look directly below, which is like on the other side of Earth, it's called the nadir. And so you really can't see that. The celestial equator is simply a projection of the equator on Earth onto the sky. That's our celestial equator. And that comes into play particularly for the equinoxes. When the sun crosses the equator, we have the fall or the autumnal equinox. When it crosses the equator on its way up from the southern hemisphere, we get the vernal equinox. So the celestial equator comes into play in explaining some other factors, including the Tropic of Cancer and the Tropic of Capricorn. So that's just some terminology. And if you were to look at the North Star, we see the Little Dipper, which is Ursa Minor. It's the little bear, sweeps away from the North Star. The end of the handle of the Little Dipper is where the North Star is, which is, like I said, about 3/4 of a degree off dead center. And we were talking about magnitudes. I'll just point out this star right here. I don't remember its name, but this star right here is a 5th magnitude star, meaning it's pretty faint. And if you can, on any dark, clear night, see all 7 stars of the Little Dipper, it's a real good night for viewing. Because as I said, this corner star of the Dipper part of the Little Dipper is magnitude 5. And when you look at that and you realize there are stars that you can barely perceive that are 2.5 times fainter, it gives you some appreciation that, hey, this is really a good night for looking at stars. Ursa Major is the Big Bear. This is the Big Dipper. And you can see again the stars Merak and Dubhe or Dubhe. If you make a fairly straight line, it brings you to the North Star, which is an easy way to find it. But you can see the motion is counterclockwise around the North Star. Then, if you look at, and this is going to answer that earlier question, so you see the sun's in the middle, and here we have in this pinkish, red, purplish, magenta ellipse is Earth's orbit. And out in the outer white ellipse are constellations. And the constellations chosen here for illustration, and there's a reason why they're the zodiacal constellations, the constellations of the zodiac. All right. So here's the sun, and here's here's Earth. So we're in the summer, we're over here. Earth is like over in this area here. So we cannot see Gemini right now because the sun is in the way, right? If we're over here and we wanted to see Gemini, we would have to look through the sun, which we can't. And so in the winter time, the constellation of Canis Major, the big dog that the star Sirius is part of, is over in this area here. Kind of, it's not exactly on this because this is again the ellipse of the zodiac, if you will. So Orion is like down here-ish, okay, and Canis Major is down here-ish. Okay, the big dog where Sirius is. So let's just say Sirius is down here. All right. So in the summertime, we can't see it because we're over here and Sirius is on the other side of the sun, not opposite the sun, but on the same way we have to look through the sun to see Sirius, and we can't. So we cannot see Sirius in the summertime. In the wintertime, let's look at January, right? Here's a convenient Earth, January 1st. So in January, in the daytime, we cannot see Sagittarius because the sun is in the way. But opposite the sun, on the other side, at night, you can see on the night side of Earth, we can see Sirius on January 1st because it's against a dark sky and the sun is on the opposite side of Earth, and we can see Sirius easily. And this circle or ellipse is the ecliptic, we call it. It's the pathway of the sun around Earth, or technically it's the path of Earth around the sun, but we're on Earth, so it looks like it's the path of the sun through the sky. And the sun goes through these constellations, which are the common constellations of the zodiac. Questions? I can stop there because this is kind of a cool point, I think, as to why we only see certain constellations at certain times of the year. And remember, it takes 365.24 days for Earth to orbit the sun, which is very close to 360, right? There's 360 degrees in a circle, 365.25 days in a year, which means Earth moves about 1 degree every day on its way around the sun. So that's why the sky changes by about 4 minutes. Every night, the sky changes by about 4 minutes because Earth is moving around the sun about 1 degree every day. And here, That bluish line represents the ecliptic or the path of the sun. And this is a very fisheye view up north. I think it was in Norway somewhere. But you can see these are the boundaries of the constellations of the zodiac. And this illustration just shows the sun is in Aries. And the sun will be following this line in the course of a year, moving about 1 degree from day to day. A lot of words here. Just point out the planets appear to be close to the ecliptic. I'm going to show that to you. Pluto can get as far as 17 degrees away from the ecliptic, and that kind of is one of the things that caused eyebrows to be raised. Currently, it's very close to the ecliptic. Jupiter is in Sagittarius. I'm going to show you that in a minute. Magnitude negative 2.5. Mars is in Pisces. Magnitude negative 2.5. I told you about the opposition on the 13th. Closest approach is on the 6th. Saturn is also in Sagittarius, magnitude 0.5. And Pluto is between. You can't see it because it's a magnitude like 14. So you can't see Pluto. But you see Jupiter and you see Saturn. Pluto is almost right in the middle. This morning coming up, which would be actually Saturday morning, don't miss it. If it's clear, and if you can get up a half hour, an hour before the sun gets up, Venus is going to be right next to the star called Regulus in the constellation of Leo. Venus is blazing, negative 4.5 magnitude. Regulus is about a magnitude 1 star, and that'll give you a real side-by-side glimpse of how bright negative 4.5 is compared to magnitude 1. But that's just very rare, and so take an opportunity to see that. All right, so I'm going to go to the night sky here, and I'm going to have to push a couple other buttons to make that happen. So bear with me for a moment, and then we can take some more questions. I'll show you some things, and then you can ask some questions. All right, hopefully you're still seeing my screen. And this is the way the sky looks in Concord right now. Right now, at almost 8 o'clock, looking south. So you can see the red S down the bottom. We're looking south, and there is Saturn and Jupiter. Jupiter blazing negative 2.5, Saturn about a 0.5. Right in between that you can't see, but you just know it's there, is where Pluto is. So we talked about some constellations. And we talked about asterisms. So this is the way the sky looks right now. If you were to go outside in Concord, this is what you're going to see right now. Here is a teapot. Do you see the teapot? Here's the body of the teapot. There's the lid. There's the little knob on the lid. Here's the spout. Over here is the handle. So that is an asterism. It's a familiar shape made up of stars that happen to be of the same constellation, Sagittarius. And notice we have coming out of the spout, this smoky looking, which is the Milky Way. And what we're seeing here is the thick part of our galaxy. We're looking, in this case, in the summertime, in early fall, we're looking towards the center of our galaxy. And that's why there's so many stars. In the winter, when Orion is out, we look at the Milky Way, we're looking out to the outer edge of our galaxy. So this is pretty cool. So Jupiter and Saturn are in Sagittarius. So let me show you the Centaur Archer here. So it's a big constellation. Then as we come to the left, we have Capricorn, we have Aquarius. I'm going to take a peek. It's 8 o'clock. I'm going to swing over to the east, and let's see if Mars is rising yet in the east, okay? Let's swing to the east. So basically I'm standing in my yard and I'm just turning my body to face east. There's southeast. Oh, look, do you see it? This is a tonight only look. The moon and Mars together, just rising right now. If you wait an hour or so, you will see them getting higher in the sky. And again, as we approach midnight, they'll be even way higher. So this is tonight. Tomorrow night, it's not going to look like this. Tomorrow night is this. That's tomorrow. Tonight is like this. So enjoy that. This is the constellation of Pisces, the fishies, right here. And then you can see, I'm going to just pull the screen down a little bit, and you can see the great square of Pegasus that we talked about earlier. Pegasus, the flying horse, is over here, upside down. This is the star Alpheratz, right here. Actually belongs to Andromeda. Andromeda swoops over this way. And so you can see like this. Pegasus, the flying horse, over here. Andromeda, the daughter of King Cepheus and Queen Cassiopeia. We're going to talk just a little more about Andromeda as I close, but I've got time for questions, so I'm not going to let anybody, leave without your question answered, or at least attempted to be answered. So that's what I wanted to show you of what is happening right now in the night sky. So when we're finished, go outside, and tonight is the night to see the moon and Mars so close together. It's not going to be tomorrow night or the night after. It's tonight. Okay, I'll pause there, and maybe you have requests or questions. I'll take questions.
Yeah, Dave, we have a number of questions. Some of them are about specific things, so I'll hit those first. And then others are a bit more about a general approach. So first of all, where in the sky in the morning do we look for Venus?
Okay, let's just do that. We can do that right now. The answer is to the east. We're already looking east. So in the magic of my computer laptop here, we're going to advance time. And so you can see things moving, right? And the moon and Mars are rising. Maybe you can see the time ticking away at the bottom. It's 10:30 now. It's 11 o'clock. And then they get really high. It's midnight now. There's Orion. I'll just stop here just for a moment. It's 1:30 in the morning. And here's Orion. And as we go a little further, the star Sirius that I was talking about is going to show up. And there it is, rising in the southeast. And this is 3 o'clock in the morning. You can see Sirius. That's the brightest star in the night sky, Sirius. And we'll keep on going. And there it is. You see it? 4 o'clock in the morning, right here. Venus and Regulus, those two stars right there. This is 4 o'clock in the morning, so maybe, and the sky is dark then, but depending upon your eastern horizon, maybe you need to wait a little longer to maybe 5:30. So you get some height. So Venus and Regulus are a little higher above the horizon. So still pretty dark at 5:30. Used to be light at 5:30. And there you see Venus blazing. You can't miss it. So just look east, 4 o'clock, 5 o'clock in the morning. You're not going to have to ask, well, which one is it? You'll know. But right near it is Regulus. And again, that's going to change. Tomorrow, the next morning. Tomorrow morning, this is what it looks like. The next morning, you see, Venus moves away. So this is another, hey, tonight, which means like early this morning. Catch it now. because tomorrow, the next morning, which is Sunday morning, it's going to be this. And then Monday morning, this. Now, that's still beautiful. I mean, it's still very bright Venus, but it's just so rare to have Venus next to a bright star that close, like it's going to be 4 o'clock, 5 o'clock this coming early morning. So hopefully we don't have fog or clouds. Okay, so that hopefully answered your where do I see Venus question.
So let's say that someone is interested in seeing the night sky, but maybe where they're living right now, there are a lot of lights around them for streetlights or something like that. Do you have any recommendations for places in New Hampshire, Vermont, or Maine for dark sky viewing?
I don't know much about Vermont. I know there's not much there, so it's probably pretty good most anywhere. There are a few, you know, towns, you know, you got Burlington, Rutland, and such. So, I mean, there's a few towns with some lights, but I would say probably Vermont-wise, you're probably in pretty good shape out many places. Probably 90% of Vermont is probably good viewing. And the same for Maine. Now, we have obviously the eastern corridor of, you know, I-95 and Route 1 and all that goes through all the major cities and towns that are over towards the coast. So you want to stay away from those, but Maine is a big place. And if you get, you know, 20 miles or so away from the ocean, away from I-95 and Portland and Augusta and Lewiston and Bangor and places, you got a bunch of dark places. Cadillac Mountain in Arcadia is a favorite place for some people to go. It's dark there. Mount Katahdin, near there, you don't have to climb it, you can, but in that area is also a popular area. New Hampshire, obviously that's where we are. We've got Nashua and Manchester and Concord and Laconia, Littleton a little bit up there, Plymouth a little bit, but there's a lot of dark places in New Hampshire. Some that I know of. I'm kind of surprised at this one, Joppa Road in Bedford, which is near Manchester. I'm surprised that it is dark as it is, but it's dark there on Joppa Road in Bedford. Washington, the town of Washington near Hillsborough, very dark there. Mount Kearsarge would be a great place to climb, or you can drive up most of the way. That's a great place. The Kangamangas Highway. You know, there are observation places where you would look at the mountains, you'd look at the leaves, leaf peepers will be there. Well, bring your binoculars, bring a telescope, or just go up there. It's dark on the Kangamangas Highway between Lincoln and North Conway. Crawford Notch, Hart's Location on Route 302 near Bartlett, Attitash, right? That's this famous ski area up in that area. Very dark there. So anyway, those are some ideas of dark places to go.
Awesome, thank you. We have another question that I think I know the answer to, but I'm sure you have more details. The question was, when was the last supernova visible to the naked eye? And I think that was 1604, is that right?
1051 is coming to my mind. You might have another one that you know about that you heard of. Maybe I'm thinking of the Crab Nebula with the Chinese in 1054. Okay,
yeah, I feel like when Betelgeuse was having its dimming period, people kept referring to 1604 as the last time that there was one.
Okay, that's something worth looking up that I would look up. I'm not aware myself of that date, but yeah, that's another interesting thing about Betelgeuse, the brightness changing, talking about magnitudes. That definitely changed the magnitude of Betelgeuse.
Then we have, I'm going to combine a couple of questions because I feel like they're all getting toward the same idea of when you go outside and you start looking up at the sky, kind of how to approach it so that it feels like a manageable thing to figure out what you're looking at. So one person had said, what program are you using? And I think maybe you're using Stellarium here.
Yeah. Yes,
But also, what apps would you recommend? Or let's say that we're talking about a child going out for the first time and looking, you know, is there maybe a way to introduce them to the sky so that it feels like they can really start to find things on their own?
Okay, great question. So yes, I'm using a program called Stellarium, stellarium.org. It's a free download. There's also a web version that you can just use it directly from the web. There's a version for your cell phone, your smartphone. I heard rumor that that's a few dollars for that one, I've heard. Then there's Google Sky, which is an app for your phone. That one of those that you just kind of hold your phone up and it's almost literally like a window to the universe. So those are a couple ideas on that. In terms of first approach, I think I would go with the Big Dipper. And so let me back up in time to a user-friendly time that, you know, it's dark but not excessively late for little ones. So I'm going to do the unthinkable and go backwards in time. Okay, so we're kind of moving along here. It's now 2 o'clock, and I went way too far. This is this afternoon. All right, so yeah, this is good. So this is 8:30 tonight, which is, I don't know, we must be, it's about 8:13 right now. So this is 8:30. So let's just swing around to the north. And so you can see here, we're looking north. Here's the Big Dipper. And there's Ursa Major, right? There you see the Big Bear. And then you see the Little Bear, the Little Dipper. So let me get rid of the artwork. And obviously the lines aren't up in the sky. We'll just leave them there for a moment. So you can see how these stars connect to make the bear. And that's one of the, I think one of the several constellations that you can make look like what they've made it look, right? I mean, you can picture the head of a bear, the back, you can see some front legs here going behind that tree, some back legs here, front legs here, a belly of the bear, an elongated tail, which goes with some mythological story. So that's kind of cool. I'm going to take the lines away. And so when you go out at night and you look north, again, this is tonight, 8:30, close to the horizon, just a little bit to the left of north or to the west of north, you see the Big Dipper. And it's pretty easy to point it out. And then you take the two stars at the end of the handle of the Big Dipper, Merak and Dubhe, and you go roughly 5 times that distance, but it's going to be the first fairly bright star you bump into, and that's Polaris, the North Star, magnitude 2. And then you can see the Little Dipper. Again, this star right here is a magnitude 5. So if you can see all 7 stars in the Little Dipper, it's a good night. Then, if you keep going from the handle of the Big Dipper through Polaris, you come to this W shape over here. And this W shape, that's the Queen. That's Cassiopeia, or Cassiopeia, or Cassiopeia. I've heard it pronounced all 3 ways. That's the Queen, this W shape. or an M, or a 3, or an E, or a capital Greek sigma. So she's on her throne, and this is, I'll just pull it down for a second here, and there's the king, and there's the queen. And so that's a place that I would start, is looking north. Get the Big Dipper so you can find it, find the North Star, see the Little Dipper, which is going to, you know, be good to see some dimmer stars. And then the W is going to be easy for you to find, which is across from the handle of the Big Dipper. So that would be my suggestion. Start with the North Sky, because the neat thing about these constellations, they're called circumpolar constellations. They go around the pole. They don't set. They're up all year round. So any night you can go out. If it's dark and clear, you can find the Big Dipper. It's somewhere. So was that helpful?
Yeah, I think so. And I think there's also maybe a follow-up bit to that. If someone was getting used to their telescope, would you recommend starting in the northern sky as well for something like that?
Well, I'll tell you one thing that is usually my first go-to with a telescope, besides the planets, because, you know, planets are always a wow factor. They're easy to find. They're bright. Again, Jupiter, Saturn, Mars, you cannot miss them. Venus, you cannot miss it. So those are definitely reasonable places to start with a telescope, is looking at planets. And then, of course, the moon. And by the way, just as a quick aside, a full moon is the worst time to look at the moon. It's bright, it's big, but the light, it's basically a position of opposition that we talked about earlier. The moon is opposite the sun, so the light from the sun hits it. There's no significant shadows and such, but a quarter moon, a waxing or waning gibbous moon, crescent moons, they show so much more detail, because it's really neat. The other night I was out with some of my students, and to be able to look at the moon, the terminator line, which is what separates the light from the dark, and you look through the telescope and you see, oh my goodness, in the dark part of the moon, you can see the sunlight catching mountaintops. You can see craters that have one side of the crater is lit and the other side of the crater is dark. All that to say, the full moon is not when you want to look at the moon. You want to look at the moon when it's plus or minus from the first or third quarter. But anyway, so telescope, planets, moon, easy go-to stuff. But in the North Sky, one of the things that I like to show people through a telescope, getting back to the Big Dipper, you see this middle star of the Big Dipper? It's actually 2 stars. Let me take down the artwork here. And it's 2 stars. Mizar or Mizar is the larger one, and Alcor, not to be confused with Al Gore. Alcor, A-L-C-O-R, is the dimmer one. And I can play telescope with my computer. I think I can. Give me just a momento, and let me find what I need to find here. Let's see. I'm just looking. There. Okay, so I've zoomed in. So here's the Big Dipper, and there's the names of the stars popping out, which is nice. But you can see here Mizar or Mizar, and you can see right next to it, there's another star right there. And you can see that easily with the telescope. Binoculars can do it. If you're really good, you can do it even with the unaided eye. So that's a place that I would look. And then coming up soon in the southern sky is going to be, let me swing around to the south. You have the Milky Way to look at. You know, you've got Jupiter, Saturn. Have a look at the Milky Way. You know, it's not a cloud. Those are individual stars. And when you look through a telescope, you'll be amazed at all the stars there that you can see. But another thing, as I mentioned about stars' color, look at some stars and take some time to notice the color through a telescope. So my first suggestion is to look north, do planets, moon, in the north sky, the Big Dipper, that star in the middle of the handle of the Big Dipper. And then I have something else for you that I'm going to show you in a moment that I'm going to kind of close to end with. So let me see if you have some other questions first.
So there was a question, you and I had talked briefly about this right before, but about space junk and whether or not that impacts what we see.
Yeah, space junk is really proliferating. And so we have an anniversary coming up on Sunday, October 4th. What's the year of the anniversary? 63 years, I think. Am I doing my math right? 1957. Sputnik, October 4th, 1957. There was only one piece of space junk going around Earth. It was Sputnik, launched by the Russians. And now there's tens and tens of thousands of pieces. So does it affect our viewing? In general, I would say no. If you really want to get technical with a telescope and a camera and take some pictures, there are what are called the Starlink satellites. They're really small, but they are hundreds of them. And they kind of go in swarms. They're like swarms of bees. They're really small, but there's a lot of them. And I've heard it said that sometimes when somebody's looking, the reflection of the sun is bothersome, and it can spoil particularly photographs. I think when you're just looking with the unaided eye or binoculars, it's not an issue. And in general, it's not a big deal yet. But the problem is they have hundreds more of these small Starlink satellites that they're planning on launching. So it's going to get worse. Not a huge deal right now, but doing some really fine technical photography, it might be a problem, but it's going to get worse. All right, is that the end of the questions?
I think there was the one more question that we had about photographing the Milky Way on nights without a moon.
Yeah, so I can only give you a general answer about photographing the Milky Way when it's dark and there's no moon up. First off, use a tripod. Secondly, a lot depends on what ISO you're using. Are you using 100, 200, 400, 1600? So that makes a difference of how long of an exposure you're going to take. The thing to do now these days with the digital cameras that we have and the SD cards that hold thousands of pictures. I mean, back in the day when I first started astrophotography, you put in a roll of film, you got 24 pictures, and you better be careful and choose them right, because it costs you 10 bucks for the roll of film and it's going to cost you 15 bucks to get it developed. So it's costing you $25 to to get 24 pictures. Expensive, but now thousands of pictures for $15 to get an SD card. So take a lot of pictures. What I would say is experiment, but keep track. You know, maybe your camera keeps the data track for you and the info, the more information for, you know, each picture you take. But also it can be handy to keep it in a notebook. Okay, picture number 100, I took at ISO 200. It was a 2-second exposure at f4. And you know, the smaller the f number, the wider the opening, so you're letting more light in. And obviously the longer exposure, the more light you're letting in. But the longer the exposure, remember, Earth is spinning. Earth is spinning around its axis always. At the equator, it's going 1,038 miles an hour. I think here in New Hampshire, it's somewhere around 800 miles an hour. So you want to keep that in mind. So a tripod, definitely. And if you can get hold of a star tracker, or you can mount your camera on a telescope that has a clock drive that, you know, keeps everything focused on a particular star. Even when Earth is spinning, you can take longer exposures that way. So those are my suggestions. The big one is experiment.
Fantastic. Thank you for answering all those. I think we've hit just about everything that people asked. But I know that Dave is always happy to answer other questions. So if you're like me and you're the kind of person who finishes watching something and then thinks later about what I should have asked, you can always contact him. You can find his email at starhop.com. Just look at under who we are. And you can send him a message, and I'm sure he'll do what he can to help there too.
I have a finale. I'm going to stop sharing this. Oops, I don't know if I wanted to stop sharing the whole thing or not. Hang on a moment. Let me get back into sharing. I have something else I want to close with. My goal was 8:30, and we're pretty close. Okay, so I need to get rid of this, and I want to bring back this and make this big. Okay, so we were talking about stars. How big are they? Here's the sun. It's amazing. Here are the planets. Compared to the sun, here's Earth. Pluto is like a pixel on the screen here. But we're going to talk about stars and how big they are, and a couple of the stars that I named for you already. So that's how big our sun is, and this is how big Earth is compared to our sun. You can get about 109 Earths across the face of the sun. You can put 1.3 million Earths inside the sun. So now here's our sun over here on the left. And now Jupiter is 1 pixel in size. Here's that star Sirius, right, in the winter sky. Pollux is one of the twin stars. Arcturus, we didn't talk about. Arcturus is not really findable with a dark sky. It's pretty light where Arcturus is. Arcturus is a spring star. A wonderful star. It's bright. It's a magnitude 0 star when it's out, and it's big. You can see how big it is compared to the sun here. Arcturus is a big star, but you ain't seen nothing yet. Check this out. Here's Betelgeuse, right? That's the upper left star in Orion. And look at our sun. Now our sun is 1 pixel. Here's Arcturus that looks so big. Right, the slide before, Arcturus looks so big there, but now Arcturus looks about the size that Jupiter did before. Rigel, lower right star. Aldebaran, I mentioned, is an orange star. That's the eye of Taurus. But check this out, Antares. This is the heart of the Scorpion. This star is so, so big. If you were to take the center of our star, the sun, whose name is Sol, and put it at the center of Antares, Mercury, Venus orbit, Earth orbit, and Mars orbit would all be inside of this star. That's how huge that star Antares is. Another question, how far away? And we're going to get back to that Andromeda and what is known as the Andromeda Galaxy. So Cassiopeia, I showed you how to find that. So off to the left is where the North Star is, and off the computer screen is where the Big Dipper would be in this image. But you notice there's an acute angle and an obtuse angle in Cassiopeia. And if you take the acute angle, which means it's less than 90 degrees, it's the narrower angle, kind of makes like an arrow. And this is Alpheratz, right? The Great Square of Pegasus is over here. There's another star, and one is off this picture. Another star is here. This is Alpheratz. Remember, it shares a star with Andromeda. And here is the Andromeda Galaxy. It's the furthest thing away. And this is the other thing I would have you do with your telescope, because this happens nicely in the fall. This is the time of year to do it. So with a telescope, you get that smaller angle of Cassiopeia. It's going to point to it. You'll see it. If it's dark out without a moon, you'll see that fuzzy spot with the unaided eye. But at binoculars, a small telescope, it's awesome to look at. And how far away is that? 2.5 million light years away. And this is the Andromeda Galaxy. This is what you're looking at. You're not going to see it like this through your small telescope, but this is an actual photograph of the galaxy that you are looking at in the Andromeda Galaxy. 2.5 million light years away, traveling 186,282 miles per second. That's like going around the equator of Earth 7 times in 1 second. Going that fast, it takes like 2.5 million years to reach Earth. So pretty cool stuff. And that concludes my presentation. And I hope that you enjoyed it. And I'm happy to answer questions now, or you can send them. Mirka shared my StarHop email. This is my personal astronomy email, astromannh@gmail.com, and I'd be happy to entertain your questions. Happy to deal with any questions now, or whatever you think. So that concludes what I have to share with you. Mirka, I'll hand off to you.
Thanks. I apologize for any noise. I've got a struggling infant in my arms right now. But it does definitely, he is way past his bedtime. But there is a hand up. George, it looks to me like you have your hand up. So I'm going to try to unmute you on our end. So hold on a second. And I think now, George, if you try to talk, if you unmute on your end, you can talk.
Can you hear me?
Yes, I can, George.
Listen, I want to thank both of you guys. You did a wonderful job. I'm sitting here with my wife, who she's interested, but you really piqued her interest. Thank you very much.
My pleasure. Thank you for sharing that. That's an encouragement.
And I think that covers everything. Emily had said, are there any other apps that can be used? But I believe that you mentioned a few already. I don't know if you have any others to add.
Those were the big ones that I would suggest. Stellarium is a big one because you can use it on your laptop, your desktop, your phone. Google Sky is one. And one of my students had another one. I just can't remember what the name of it is, but it was pretty decent as well. You can probably just Google sky apps or something like that, and probably a bunch of different ones will pop up for you. I just happen to be a Stellarium fan, kind of landed on it. I love it. So I really haven't tried many others, but I am aware of Google Sky.
That's good.
And then we have one final question that just came through, which was, to what extent are the space photos we see true color versus false color when we talk about like space telescopes?
Well, and that's a great question. Hopefully, the pictures that you look at, you know, in their original source, like Astronomy magazine or Discover or National Geographic, or if it's on a TV PBS program, hopefully they tell you that. Because you're right, there are so many images are false colored, not to deceive people, but because they use the colorization to stand for something, whether it's a temperature or an elevation, or they may enhance the color to bring out like chemicals or elements. Typically, they may enhance the colors so like the greens and the blues and the magentas show up more vividly, and green typically is a color they assign to oxygen. So the colorization is not to fool the public. The colorization is to help scientists be able to visually see data in front of them represented in color. But for you to know what a regular, so to speak, white light photograph is, in theory, they should say that with the photograph and tell you if it's a band of the electromagnetic spectrum in particular, ultraviolet, infrared, enhanced color, or if it is, you know, a regular, so to speak, white light photograph.
Okay. Thank you so much for all of your information and time and enthusiasm tonight. I think we've hit all of our questions.
Great.
But as I said, if we have any others, you can always contact Dave, and he's happy to answer them or figure out someone who can answer them. Just for those of you who haven't been to a virtual Superstellar Friday with us yet, just know that tomorrow you will be getting an email thanking you for attending, but also asking for any feedback that you might have. We're also always looking for suggestions on topics, things like that. So if you have questions or comments, please feel free to pass them along to me. And I'm gonna go take this little one. So Dave, I will leave it to you to end the meeting tonight. Thanks.
Okay, well, Mirka, thanks for putting this together and inviting me to share. So thank you all for coming. I enjoyed it. Great questions. I'm glad so many people hung on for so long, for an hour and a half, now a little bit plus. And I will be in person if you want to come by and say hi. I will be at the McAuliffe-Shepard Discovery Center tomorrow. I'm doing the 2 o'clock tonight Sky Show in the Planetarium Theater. I'll be there all day, and love to meet some of you folks. So last call, any questions? All right, so this is Dave McDonald, astromannh@gmail.com, signing off. Have a great night. And don't forget to go out and look at the moon and Mars. And then in the morning, check out Venus and Regulus. This is the night to do it. Okay? See you later. Bye-bye. Just watching people flitter away. Okay. Bye-bye.